host session. So the first person that we have for this leg is Ji-hoon Kim. So please start.
Okay, so we're looking for the microphone. I'm just gonna use this one. Okay, so thank you very much for the introduction. My name is Ji-hoon Kim. I realized that this is gonna be my first time to talk about anything other than the Agora project in this workshop in 7 years. So as many of you may know, I'm still the Agora project coordinator because nobody else wants to do it. So, I mean, it's going great, and we're going to have a terrific weekend workshop, and Joel and Santi is going to talk about it tomorrow. But today I'm going to talk about the other research that I'm doing, including the simulations of supermassive black holes. So in the first part, I'll talk about the sophisticated multi-scale numerical experiment. I mean, we heard already about the illustrious TNG and the fire results, but I'm going to present you with some results from the adaptive mesh refinement called ENSO. And if I have time for like 2-3 minutes, I also am hoping to talk about the application of machine learning. Yes, of course, yeah. So now that I have a new job in a physics department, physics program of a university, I get to talk to a lot of smart people, but who may not have a full context of the astrophysics and cosmology, but they have a good reference point now because of the recent observations of the LIGO binary black holes, and also the visualization of the event horizon by the Event Horizon Telescope. So because they have a good 2 reference points, I get to say that, tell them to make a, PDF, probability distribution function of black hole masses of all the known black holes. And you can see that there will be 2 peaks, stellar mass ones and the supermassive ones. And then I can tell them that what I do is to study what happens before these supermassive black holes are made. Is it from a stellar mass seed black hole, or is it from somewhere else that is not yet observed by us, probably because of the observational bias we have. That's a great way to talk to a layperson in my field of research. So that's a start. And in this particular audience, I don't think I need any to convince you. I don't think I have to convince you that the high redshift supermassive black holes are important. So when I look at this topic, there are a couple of questions that the high redshift supermassive black holes are raising. And these questions are important if you are trying to design a simulation, because unless you can simulate the entire universe for unlimited amount of time to cover every single phase of the evolution of the supermassive black hole, you probably have to target your simulations carefully around a certain specific questions. I want to sort of go over at least the first 2 ones. So first is what seeded the high Z supermassive black holes. I mean, there are different scenarios, but as you all know, many of you all know, there is a scenario starting with the stellar mass POP3 remnant black holes, and also there will be a other scenario called direct collapse black holes, or supermassive stars, or more massive seed scenarios. So either way, you have to be careful, what you're hoping for in your simulations. Second question, how did these supermassive black holes grow after it is seeded by either of those scenarios? I mean, is it by just a, sub-Eddington or some kind of super Eddington accretion, or is it by augmented by a merger of black holes or the merger of galaxies? So this is the second question. So as I look at this list of questions again, unless your simulation can cover the entire period, starting with the stellar mass seed to the, say, billions of solar masses of end results, you have to focus your simulations around, for example, around the phase where it's seeded by a stellar mass black hole, but grow, say, into a 10 to the 5, 10 to the 6 solar masses black hole, because there is a resolution that you can use to cover that limit, and then may be a little too high to cover the later phase of the evolution of the supermassive black holes. So in the talk that I'm going to present later, I'm going to focus on the second part, the second question. So once you have like 10 to the 5 or 10 to the 6 solar masses of black holes, what happens after that? Is it just easy to create a 10 to the 9 solar massive black holes just by a Eddington limited accretion, or do we need something else? I mean, it has been the focus of my research for many years, and I'm going to give you a sort of schematic overview of what are the players in this game, and these are, of course, the known players: supermassive black holes, gas, and stars. What I want to focus is that to correctly describe the accretion and feedback of the supermassive black holes here, the arrows up and down between gas and the supermassive black hole, the massive black hole accretion and feedback processes. What actually you have to understand is that the competing channel of gas consumption, that is between the gas and stars, the star formation and feedback, it also has to be correctly described, because it's the competition, how the gas is consumed. Is it by the black hole accretion or by star formation? Unless you have a full and comprehensive picture of those two processes, the two competing processes, then you may or may not overestimate or underestimate the growth rate of the supermassive black holes. And of course, you also have to cover a much larger dynamic range than the scale of the supermassive black hole, because we are talking about galaxy mergers. That is probably a factor that can accelerate the growth of the supermassive black hole. So this is what we have in our ENSO toolbox. So this is what I have been working on for several years. So we have the massive black hole accretion and feedback physics, and there is a star forming clumps formation and feedback physics. So for the massive black hole accretion and feedback, we assume a Bondi accretion rate without the boost factor, without any Eddington limit. So that was our choice. So I just mentioned this to differentiate my work with the previous two talks. And also another factor that is slightly different from the previous talks is that I include the radiation channel of the supermassive black hole feedback. So it's the active on-the-fly radiation ray tracing with a 4 parsec resolution around the supermassive black hole. So that's done in every photon time step. So half of its energy, half of the feedback energy is through the radiation channel, and the other half of the feedback energy is through the wind channel, bipolar wind channel, which is similar to what Robert said in his talk is kinetic, or Melanie said, kinetic feedback. So that has been tested in multiple different applications, so including the mergers. I was able to see that it creates a large outflow, and also it successfully self-regulates its own growth. So to go over the other tools in my toolbox, so that is the star forming clumps formation and feedback. So there I actually also do the full 3D radiation transfer of the radiation feedback of the star particles. So each of the stars in our simulation represents about 1,000 solar masses. So that means we're going to have about tens of thousands of radiation sources in our simulation at a given time, including the supermassive black hole that I talked about. But we were able to successfully carry out this simulation for tens of millions of years in the context of high redshift supermassive black hole host, so which I'm going to talk about later in my results section. But here the UV photons do the photoionization and photoheating of the nearby interstellar medium, representing a early feedback before the supernova explosion comes into play. So as we know, this is an important channel that we have to resolve to properly describe the stellar feedback. So in this work, in my previous work, I was able to use this machinery to show how the photons escape from the galaxy, but also from each of the star-forming clumps. So these two tools, like the black hole physics part of the tool and also the star-forming clumps part of the tool, has been tested over the years, and putting all those tools together, I have been running the high redshift supermassive black hole host simulations in here. So here what we see is the most massive galaxy in about 100 megaparsec cubed box. So it's going to be at redshift 7.5. It's going to be the good candidate for the highest redshift quasars that is known to us in the universe. So I have to mention that this is the initial condition that we identified in the Agora project. So this is one application. I'm creating my own example of how the Agora project is being utilized in research. So the IC is there. You just grab it and run it. The target halo has been identified already. So this is going to end up as a 10 to the 13 solar mass, like cluster-like halo at redshift 0. So it will be a good candidate, again, for a highest quasar galaxy known to us. So when we run the simulations, it has at the around this redshift 7-ish, it has the physical resolution of 4 parsec or so, which is enough for us to run the full ray tracing to describe the nearby medium around the star-forming clumps and the supermassive black holes at the galactic core. So these are the preliminary results. Preliminary because I haven't submitted this paper yet. I was about to hit the submit button like last night, but I couldn't for some technical reasons. But anyhow, so this is, there are 3 columns. So this one has this, right column has all the bells and whistles that I talked about, the stellar feedback radiation and the supernova feedback. The second column has all the bells and whistles except the stellar radiation. So these 2 simulations are the focus of my talk in the later part of this presentation. So once you have, what we found is that once you have an additional feedback, which is the stellar radiation that we decided to include using a ray tracing machinery, which is a very expensive one. It makes the simulation go like 10 times slower than the one without the radiation feedback. Once you have that additional feedback, you may think that, okay, so this is additional feedback, so it may make the black holes grow slow, right? But it's the opposite. It's the exact opposite. So what we found is the stellar and the massive black hole feedback, including the radiations of each of those players, help the supermassive black hole grow faster because the radiation, the extra radiation, extra feedback channel from the stars make the interstellar gas around the supermassive black hole stay there without being consumed by the star formation, and it's just there. It's a little warm, but then until it eventually collapses, until eventually it accretes onto the supermassive black hole, it's a way of preventing the fragmentation into the star-forming clumps before it accretes to the supermassive black hole. So here's the PDF. It's the density and temperature. You can see that this is without the radiation. This is with the radiation. You can see that with the radiation, basically all the gas is essentially 10 to the 4 Kelvin or less. So it forms actively star-forming clumps. But with the radiation from the pre-existing star-forming clumps, it actually heats the gas up to 10 to the 4, 10 to the 5 Kelvin, makes the star formation a little hard, and keeps the gas until it falls onto the supermassive black hole. It's again, elaborated in this Tumley Q parameter. So this is the cylindrical radius from the supermassive black hole. You can see that with the radiation and all this red line, the Tumley parameter is much above 1, so making the gas very stable against the fragmentation. So this is in line with the other attempts, like for example by this gasoline, which told us that the gravitational turbulence in the merger is actually preventing the star formation as the gas flows into the supermassive black hole, keeping the gas intact until it starts to accrete onto the black hole itself, preventing. So it's a kind of a way, I guess our work is in line with theirs, in that we're trying to find a way to make the gas collapse directly onto the supermassive black hole. So that has been sort of the first part of my talk. I hope I have convinced you that this new technique, more sophisticated physics of star formation and feedback and black hole physics, has to be included as we have more and more resolution and better and better simulations to understand the supermassive black hole's growth and evolution. So if I have like 3 more minutes, I was hoping to talk about this a completely different one, how we use the machine learning to sort of replace or compensate the semi-analytic models. So we already, I guess, my students already talked about this in the 2-minute talk yesterday. But the idea is this. So if we have a illustrious TNG simulations, there is a dark matter catalog, and there is a galaxy catalog. I mean, there's a more like one-on-one correlation between them. And machine learning is really good at finding those correlations without any human intervention, without any man-made parameterization. So we train our machine to predict the baryonic properties based only on the dark matter properties in a dark matter halo catalog. And we, of course, test that baryonic properties against the illustrious test data set aside for our testing, like 10% of the illustrious data. And we use this machine now to apply to a dark matter only simulation data. I mean, we can do that. And there are lots of ways. There are not lots of reasons why we have to do it. Like, for example, if you want to study a much larger volume simulations than the illustrious TNG one, like if you want to study the baryonic BAO signal, then you may need a much larger volume simulation. But yet, you may want to have a sophisticated physics from the ones like Illustrious TNG. So we apply this machine to a dark matter only simulations, like for example, in this case, a multi-dark simulation. We get the baryonic catalog, galaxy catalog. And this is one example. So this is the dark matter halos, circles, black circles. And this is the baryonic properties from the Illustrious TNG simulations. The color means the baryonic fraction. The size here means the baryonic mass. And this is the machine predicted quantity. So this is the illustrious replications of how our machines work. And this is how the machine is applied to the dark matter only data, in this case, a multi-dark simulations. Here, what you see is the black hole mass distribution in a volume, in a density distribution. The volume density, and here the blue line is actually the SAM, semi-analytic model prediction, and the black line is the illustrious prediction. And the red line is how we, the result when we apply our illustrious trained machine onto a dark matter only data. And you can see that our machine, as designed, is better at mimicking the behavior of illustrious TNG when it colors the dark matter only simulation with a baryonic property. So it's an easy way of transplanting the baryonic physics from a high resolution hydrodynamic simulations onto a dark matter only simulation without any human-made parameterization. So I'll just leave it there, and if you are interested in this topic, just talk to me or the guy who's looking like this. Thank you very much.
Questions? Okay, here first.
Hi, Ji-hoon.
Yes.
With regard to the last point, so maybe I just missed something. Does this imply that the baryons don't affect the properties of the dark matter halos in the hydro simulation, that you can use the dark matter only properties to infer?
That's a good question, and you know, we had the comments about that from the people that we have been talking to. But we have found that you know, the variations, I mean, the improvement that we get, improvement is the wrong way of putting things here. But the differences that we get between, for example, our model and the semi-analytic model is much larger than the so-called baryonic back reactions that, you know, some are concerned. So we think it is yet too early, or our models are not sophisticated enough to be concerned about that effect yet. Yes. Yes.
Hi, Ji-hoon.
Yes.
So you talked about photoionization.
Yes. Yeah.
And have you thought about photodissociation? So you know, doing Lyman-Werner feedback to, you know, as an ingredient in black hole formation. I'm going to refer to Charlotte Christensen and Julian Bellavary and Kelly Holly-Bockelman's work on that.
I mean, obviously there
And
are...
Glenna Dunn. Yes.
I mean, obviously there are lots of physical processes that we are ignoring, especially how the photons interact with the interstellar medium. And this is just only one channel that we included, like photoionization, and photoheating, just with this 16 eV monochromatic photons. So, you know, I see that there are lots of, you know, areas to improve here. So, yeah. Yes.
Just a very brief question.
Yes.
What information of the halos did you feed the machine learning algorithm?
That's a good question. So we are at the moment kind of limited by the information context of the dark matter halo catalog. So we're limited by what the illustrious TNG people have shared with us. So for example, we include like dark matter mass and spin parameter and its environmental you know, factors, like how far it is from the, you know, the next massive halos, for example. We have like 9 different parameters or so. So maybe my students can clarify. Just raise your hand. Yes.
So we're going to have the last question while the next speaker sets up.
So I'm following up on the Nier's question. I think the baryon is important, especially the gas. I think is more the dominant component of the baryons. Do you actually also train on gas mass and temperature, and has that been implemented in your machine learning?
At the moment, no, but we are actually trying to see if how we can sort of do that in a creative way. Yeah, so we can talk about it afterwards.
Okay, so let's thank the speaker again.